Equilibrium, I think of as the dance that's happening in chemistry. When we write chemical equations, right, we write reactants with an arrow pointing to whatever products we have. This is typically how we write chemical equations and how we've written it so far. In actuality, what's happening is, right, we're going from reactants to products, but we're also going back from products to reactants, and we're sort of going back and forth. There's this sway that's happening. So these are the two ways that you'll see the arrows written, right? Most commonly this way. So it's really this sort of dance that the reactants and products are doing, right? Where we're going from reactants to products and then we're going back to reactants. So that's really what's happening if we think about what's happening in a beaker or a vial where we're actually doing a chemical reaction. And an example, there's many examples, like when we're breathing, we inhale and then we exhale, right? Also, I love the beach, right? And so the ocean is doing this same motion, right? Where the tides are coming in and then the water goes back out. So this is what's really happening also at a microscopic level in terms of chemical reactions. So, how do we define equilibrium? How do we define it? So, equilibrium occurs when the rates of the forward and reverse reactions are equal. So, even though we have this going back and forth between reactants and products, there is a point where we reach equilibrium. And this point is defined as when the rate of the forward reaction and the reverse reaction are equal. So let's look at an example. We have N2O4 going to NO2. If we write, so actually I want you to pause this video and write the rate law for the forward and the reverse reactions. So go ahead and pause it and write it. So once you've written it, this is what you should have. So the rate law is the rate constant times the concentration of the reactants. And I've just denoted K sub F to mean the rate constant for the forward reaction. And then the reverse reaction, right, is basically our products are now the reactants. So I just write K sub R as in rate constant for the reverse reaction, NO2 raised to the second power because we have that coefficient of 2 there. So at equilibrium, which is denoted here by this symbol here, this is true, right? Our rate in the forward and reverse reaction is equal. So our rate laws for the forward and reverse reaction are equal. So here I'm graphing and showing this, the rate. So on our x-axis, we have time. On the y-axis, we have rate. So the blue line here is showing the rate in the forward reaction, and the red line is showing the rate in the reverse reaction. So notice that the rate for our forward reaction, right, it starts higher and then it decreases until it plateaus. Whereas for the reverse reaction, it starts at 0, which makes sense because we start off with when we first start this reaction, right, we have to go forward before we can go in the reverse direction. So at some point, they both plateau, and this is when we know that equilibrium is achieved. And this is the point also where the two rates of the forward and reverse reaction is equal. Now, if we look at the concentration of our reactants and products, we can see that N2O4, which is our reactants for our forward reaction, we start off with some concentration, and we have zero concentration of our products because we haven't actually like pressed play and had the reaction go yet. Once the reaction proceeds, our reactants decrease because they get consumed, and our products increase because they are produced. And what we notice is that the concentration of both the reactants and the products stabilize. They both stabilize once equilibrium is achieved. The concentrations are not necessarily equal, like the rates are equal, but the concentration of the reactants and products stabilize at equilibrium. So equilibrium is dynamic, right? The reaction hasn't stopped. It's not like, okay, the reaction is now fixed, it stopped. It's still very much dynamic. It's just that the forward and the reverse reactions are proceeding at the same rate, right? So if we think about it with the breath, it's basically like we're inhaling 1, 2, 3, 4, out, 2, 3, 4, right? That rate is the same. We're inhaling to the same rhythm, the same cadence as we're exhaling. And so that's what's happening with our chemical reactions at equilibrium. Their rates of going from reactant to product, product back to reactant are the same.